on yesterday was that we looked at SN2, and we saw that SN2, if we looked at something like this, right, and added in a good nucleophile, let's say like the azide, that we can predict based on the structure, good nucleophile, that we would get this product, right? So that what's happening here is that we have a backside attack. Right, so we get this product. So SN2 substitution, nucleophilic bimolecular, the 2 stands for both groups are there in that position. Okay, and let me pull up the chat. I don't have it showing on my screen. So. All right, remember, if you have any questions or need me to stop, either interrupt me or go to the chat. Okay, so we covered SN2. Today, what we're going to be looking at is biological methylation. Large number of you plan to do health related. So we are going to go ahead and cover the biological methylation. So if we think about nucleophiles, right, it's got a lone pair, some of them are negative, right? We could have a simple methylation by just adding methyl iodide. The reason you'll see that we almost always use methyl iodide instead of methyl bromide or methyl chloride is really practical. Methyl iodide is a liquid, methyl bromide and methyl chloride are both gases. It's easier to work with liquids than gases. Right, so this is just methylation, and if I was going to do methylation in a lab, I would just go and grab a bottle of methyl iodide and start my process. Now, it turns out that methylations are specifically important in, we're in 7.5 moving forward from there. So if we look at biological systems, you've got several places where methylation is important. You can convert precursors into hormones with simple methylation. You can invert DNA strands by putting a methylation on it, which can be problematic if you don't want it there, but is important in other spaces. So methylation is probably second to proton transfer in many biological methods, right? So you'll see it a lot. So how do we do it? It's not like we have methyl bromide running around in our system. So in a biological system, you have often large molecules that do the same thing as small molecules. And here, ATP, we know that as adenosine triphosphate, right? It's this big, large molecule with this triphosphate group on it. This triphosphate is a great leaving group, which actually is one of the things that you should recognize or start to recognize now when we're talking about leaving groups and nucleophiles, is that phosphate, diphosphate, and triphosphate, this molecule, are all really good leaving groups. And one of the things that ATP does when it goes to ADP and AMP is lose phosphates by transferring it to other things. So we'll see when we get to alcohols that phosphates are actually activating groups, and that ATP activates alcohols in biological systems. In this case, what it's doing is giving us the base structure for our sulfur-containing compound, this methylene to react. Okay, so when we look at this one, we get our SAM. That's what this molecule is. And what we need to pay close attention to is this methyl group right here that's attached to that positive sulfur. The large adenine, adenosine molecule allows this to fit well in, one, it's soluble, but it's also fits well in enzymes. So if we look at then our, the comparison of our methylating agents, it's really just that methyl group there. That's what we need to watch for, right? So in the methyl, the iodine is the leaving group. In the SAM, it is this, all of this is the leaving group. So it looks like a big waste, but again, it's going to be recycled. This goes on and gets remethylated through another process. So it'll fall apart. It'll get phosphonated by inorganic phosphate, and then it'll come back and get recycled. So it's not like we're throwing the whole molecule away. It's not like the water bottle society we live in. So the body is very efficient. Okay, so what we're seeing in these then is that in a biological system, you're going to have a nucleophile, right? You're going to have this CH3 plus S, and then you've got this big, SAM molecule right there. And what's happening is that in an SN2 style mechanism, we're getting a nucleophile attacking that methyl, right? And then we get the demethylated SAM molecule. Okay. Okay. Any questions about this one? And what you'll see on practice problems here is you might see a practice problem where you have something like this, SAM, and that's going to methylate the nucleophilic position. Usually the questions around this are going to be a little bit more complex from this, but it's going to be, can you find the nucleophile, and then that nucleophile will get methylated. Okay. So again, it's a new reagent, but it's the same chemically as what we would use the methyl iodine as shown up here. So instead of moving into unimolecular substitution, we're going to go ahead and look at elimination. So on Monday, we looked at the different types, and here we're going to look at E2 eliminations. So generically, what's going to happen in a elimination is I have my base is going to react with my substrate. I'm going to eliminate a hydrogen, right, to give the base H. So the base is going to extract the hydrogen to give us an alkene. So we're eliminating the hydrogen and the leaving group. So just like with substitution, we can have a concerted mechanism. In the concerted mechanism, the base is going to come in, abstract that proton, so proton transfer. And then we're going to get loss of the leaving group. So we made a new bond to the hydrogen, right, plus our leaving group. In a stepwise mechanism, give myself a little more room here. in a stepwise mechanism, the first thing that is going to occur is loss of the leaving group, forming the carbocation, and then the base coming in, abstracting that proton, electrons going towards the carbocation, giving us the double bond plus the B and H, the protonated base. So we have concerted. If we look at the rate, since there's only one step here, the rate is going to be the substrate times the concentration of the base. So this is elimination by molecular. So again, the name comes from the rate, the kinetics, and we refer to that as E2. The rate for the second one, as we saw before, forming the carbocation is a high energy reaction. So that's going to be slow. So we get a slow reaction first. That gives us K is just the substrate. That's elimination unimolecular, right? Or E1. And we'll look at E1 when we get to SN1. This book covers SN1 and E1 at the same time. Okay. So we've got, concerted, just like we had with substitution. That was SN2. This is E2. And we have stepwise, which is similar. SN1 and E1 are both stepwise mechanisms. Okay, questions? So we're going to be comparing SN2 and E2 together quite a bit. And one of the ones to look at is substrate, right? So for SN2, we saw that methyl, right, was preferred over primary, which was preferred over secondary, which was preferred over tertiary, right? So the rate of the substrates, right? And that was because if we look at a tertiary, we've got a CH3 here, we've got our CH3 here, another CH3 in our leaving group, the nucleophile, right, needs to come in and attack that backside, but because of all the steric hindrance, we're not looking at this. So what's important is the stereochemistry around this alpha position. So you remember we had the alpha position is where our halide is attached, or our leaving group. When we look at the substrates for elimination, we're still going to be, you're still going to have a leaving group, and the alpha position is still going to be tertiary, but it's not that position that's important in elimination, because when we bring our base in, our base is not reacting with the alpha position, it's acting at the beta position. So the sterics here is not around the alpha position, it's around the beta position. And because we're not dealing with getting close, so if we think about here, we've got to get into this anti-bonding orbital. What we have to do here is just get to that proton, right? And that proton is going to be out in space. So we don't have to get to the center of any of these carbons, right? We just have to get to the edge of one of these hydrogens. So the base can come in, pull that hydrogen, right? And so therefore, oh, and I never finished, well, that never occurs because it's blocked out, right? So, so therefore, if we think about it, sterics has little effect. Which means, right, that the alpha position substrate is there's not really a difference. E2 could occur with almost any of these except what? Which of these in this methyl primary, secondary, tertiary could E2 not occur? Methyl, right? There's no beta proton, so the methyl doesn't work, right? So we can't have methyl, but the primary, secondary, tertiary, because we're looking at that beta hydrogen, that's what's going to give us the products. Okay, and this is a good time to do a try this to kind of let your mind sink into it before you shift gears. And this is a question that you'll probably see on some of the homework. I'm going to give you just a leaving group. So on this one, I'll work the second one so you can see what's happening, and then you can work the other two. What we're looking for here to figure out our E2 products is where our beta hydrogens are. So if we look here, we've got 3 beta hydrogens, right? But I can rotate all of these into each other. So therefore, how many equivalent beta hydrogens do I have? Well, I have 1 equivalent beta hydrogen here. If we look over here, I have a hydrogen there and a hydrogen there. Can I easily rotate those into each other without changing the structure? No, right? Because if I rotated these into each other, I'm going to end up with 2 different structures. So if I look at this group here, I actually have 3 beta hydrogens, right? I have beta hydrogen 1, beta hydrogen 2, and beta hydrogen 3. So therefore, I can eliminate beta hydrogen 1. I can eliminate beta hydrogen, and let's say this was up. And this is beta hydrogen 3. And then we'll get a little bit more specifics in this in a second. Beta hydrogen 2. So what I want you to identify here is how many possible products do you think these are going to have? So let's take a couple of minutes, take a look at the first one and the last one, and see if you can determine how many products we could have. And the first step is just identifying your beta hydrogens. So again, beta is 1 away from where your leaving group is going to be attached. Okay, so for consideration of time, let's look at the first one. Okay, so if we eliminate to the top, right, I could get that. And if we eliminate down to this other set of beta hydrogens, right, we have beta hydrogens here, beta hydrogens here. If we eliminate up, we get this. If we eliminate down, we get this, right? But those two molecules are the same molecule, right? These would both be just cyclohexene, right? If we look down here, now we have some symmetry between these two. So if we look along this axis, we have symmetry, which means we really have 1 and 2 and 1 and 2, which then will give us this product and this product. All right, this will make a lot more sense as we continue through, but it's important for you to start identifying your beta hydrogens. That's really what I was trying to do here. How many beta hydrogens do you see, and do you understand that the beta hydrogen is what's going to be important for you to be able to figure out your products? All right, let's step back a little bit, look at some nomenclature of alkenes, stability. We still start with the same thing. We're going to find the longest chain, 1, 2, 3, 4, 5, 6, just like we did before. So this is going to be hex. But now it's got a double bond, so we're going to call that hexene. Right, so we've changed the A to an ene. That means that the suffix of the parent name is changing. That is different. That is a difference than what we've seen before. Before we've been adding side groups, right? So methyl, ethyl, side group. Here we're changing the actual parent name suffix. That means that that parent name suffix, that ene, now has priority, right? So in this case, we could look at numbering left to right or right to left, and either way, we're going to end up with 3. Now, it's important to realize that whenever you have an alkene, you would need to go from 3 to 4. So the numbering of the alkene is always you represent the first carbon, but then the next number needs to be the next carbon down. So you wouldn't put a 3 and then jump to another part of the molecule. It needs to be sequential. So the 3 and 4 are important. I only list the 3 because the rule is the next carbon with a double bond would have to be 4. Okay. Yes, you could have either hexene, 3-hexene, or hex-3-ene. The first is preferred on simple. The hex-3-ene is preferred when it gets more complex. So if I had a lot of side groups and those side groups were getting complex, I would then want to clarify my molecule by putting the 3 as close to the ene as possible. But on simple molecules, putting the 3 in front works perfectly fine. Okay, so it's more of a preference. You'll see the 3 in front of the ene in most of the simpler names, but as these get more and more complex, you'll see the 3 being moved. Now, if you look up the IUPAC name, you'll see both of these as IUPAC names. It's a preference on when you use it. Now, this next one, again, I have a habit of drawing 6s. So 1, 2, 3, 4, 5, 6. If we go the other direction, 1, 2, 3, 4, 5, 6. Okay, in this case, remember we're naming this as an ene. So although I have 2-ene 5,5-dimethyl, and if I had done it the other way, I would have had 2,2-dimethyl 4-ene, right? I'm going to go with the preference that this is being named as an ene. So therefore, this is going to be the 2-hexene ene, right? 5,5-dimethyl. So whenever I change my suffix name, that all of a sudden makes that the preference. I want that to be the lowest. So up to this point, we've just been doing anes, right? So therefore the side groups get the preference. Now, when we see enes, we'll also see this with alcohols. We'll see this with ketones, right? As we start adding suffix names to the parent name, all of a sudden that gets priority. So this is 5,5-dimethyl 2-hexene, not 2,2-dimethyl 4-hexene, even though the 2,2-dimethyl 2,2,4-dimethyl 2,2-dimethyl 4-hexene is a lower numbering, because my preference is now the ene. I want to get it the lowest possible number possible. Okay. Questions about that? Okay. There are a group of common names that's important to know, mainly because they're still used quite a bit. Ethylene, used in polyethylene. Propylene, used in polypropylene, both commercially. And then of course, polystyrene. So, you've got styrene here. Really kept alive by the fact that their polymers are all named after their common names. But you'll see ethylene, propylene, and styrene specifically in engineering terms, but again, commercially available polymers use these names. And what the polymers are made from these substrates. So this isn't the polymer. The polymer for polystyrene is this. And it turns out that you can puff polystyrene. And when you puff polystyrene, it makes a really good insulator. So, okay. There's also some side group names. So that are very pretty common. The first one's not as common as the next two. This methylene. You'll see this whenever you have something attached to a group, right? So if you have a really complex name and you have this double bond carbon hanging off the side, especially if, let's say, it's a carboxylic acid or an amino acid, and now you got this double bond hanging off the side, that is called a methylene, right? So think about it is that if it just was a single bond carbon, that would be a methyl side group. But now it's got a double bond, so this is a methylene side group. This next one is vinyl, which of course we know not only from records, but clothing and other things, right? Vinyl is a polymer. Most of vinyls, it's a placeholder for a lot of different polymers, but vinyl is this side group like this, and then this other one, which we'll see, both gives a reactivity part. We'll see allele stability, right? We've talked about that with carbocations. We'll talk about it more with carbocations. This is an allele group that's attached. And it is important for this isn't a large list of common names. It is important for you to know these common names. Stability, the first thing we need to think about with stability is how do we classify our different substitution patterns. And we'll call this mono substituted, di substituted, tri substituted, and tetra. And if we take different, substitutions, and we burn it, we can get different combustion energies, right? And this combustion energy can tell us something about the stability of these different molecules. And what comes out of this is, do the electronic stability of the hyperconjugation, the tetra substituted is going to be more stable than the tri-substituted, which is going to be more stable than the di-substituted, which is more stable than the mono-substituted. And then also, if we look at the trans, is going to be more stable than the cis. So this is referred to as the trans, this is the cis, right? So trans is going to be on opposite sides, cis is going to be on the same side. And this has to do with the hyperconjugation of the electronics. There's also a steric effect here, but the steric effect is less I'm sorry, that's a question to the group. So if we look at the substitutions here, that means whenever we're making these reactions, there's going to be difference on, oh, sorry, squiggly bonds. Okay, that one is a question for me. Squiggly bond here means where that's a broke. So if we were looking, let's say at the vinyl, let's say that we had something like this, right? This could be referred to as the vinyl. So what I'm showing you is not what's attached. I'm not showing you this, right? That squiggly just means where it's attached. Okay, that is a good question. Thank you. All right. I don't know if there's a new group me. If you want to add me to it, feel free. Okay, so tetra, tri, di, and mono substituted. Okay. The other thing to look at is cyclic alkenes. And misspelled it.
There's a question in the chat that I'm kind of wondering myself.
Mm-hmm.
About nomenclature, it's saying, is 3-hexene the same as 3- or hex-3?
Yeah, we covered that one up here. So you may want to run the video back a little bit. Yes. Usually when it's simplified, right? When it's a simple molecule, you use the 3-hexene. When it's more complex, you'd use the hex-3-ene, right? So if it had lots of substituents, I would want to move the 3 closer to the ene. So you'll see these used pretty interchangeably. The preference for simple molecules here is 3-hexene. You wouldn't see hex-3-ene written out. It's just too simple. But once you get to really big molecules, you'll see complex molecules. You see that the number for the ene moved next to the ene. So for this level of molecule, I probably would not call this hex-3-ene, but it's more of a preference. Both are IUPAC.
Okay.
Okay. All right, so if we look at cycloalkenes, okay, we have our different structures here. And I don't know why I couldn't draw a square. And if we look at the stability, remember that an sp2 wants to be 120 degrees, right? So the carbon wants to be sp2, but if we look at a triangle like this, that's got to be 60 degrees, right? A square is going to be 90 degrees, and then we get 120, right? Wait, 105, forgot my geometry, 105, right? And then 120. So when we add double bonds into these cycloalkenes, we see that we get even more strain than what we would have gotten for an sp3, which is 109.5, right? Except for the alkene, I mean the cyclohexene. The other thing to realize in nomenclature of these is that we use, again, we're naming this as the cyclohexene. So this is going to be 3 methyl spelling cyclohexene. Now notice I'm not numbering where the ene is. Why is that? Well, ene gets preference. If the ene gets preference, then what is its number? Well, its number is going to be 1, right? I'm in a cyclic. But what we said about enes before is that enes always need to be consecutive. So therefore, it needs to be 1 and 2, which means the methyl then becomes 3, right? So when we the nomenclature for cyclic alkenes needs to take into effect that we have that the preference is the ene, and then the double bond, the ene needs to be 1 and 2. Okay. The other thing with stability, so if we look at it, you know, this is going to be much more stable because 120 degrees, and that matches the sp2. If we look at other items, right? So let's say we get to, I'm fixing to draw a 6 and I meant to draw an 8. Right, I could put a double bond like this, a cis double bond in an 8 ring, but if I tried to do this, do I have enough carbons here? 1, 2, 3, 4, 5, 6, 7. Oh, 1 short. If I tried to do something like this, right? Right. I have a big difference in whether something is cis or trans. If I look at my 3, 4, and 5 here, there's really no possibility for trans. It's always going to have to be cis. When I get to larger rings, the cis, depending on the ring structure, right? If I got the incredibly large rings, you might be able to have a trans that is pretty stable. But even when we get up to ring sizes of 8, the cis would be a stable molecule, and this cyclooctene is a pretty common molecule in the cis form, but the trans is not. Right, the trans just is really very unstable and will react very quickly to try and stabilize itself. When we look at E2, we need to look at regioselectivity and stereoselectivity. So if we look at this group, we have 2 possibilities. We could eliminate to the primary, we could eliminate these hydrogens here, and let's go ahead and draw them in. Right, I could eliminate these hydrogens. And if I lost one of those hydrogens, right, with my base, I'll end up with the top product. If we look at the other beta hydrogens, right, we end up with these 2 beta hydrogens. And so if I lose one of those hydrogens, then I would end up with this product. Now, looking at these 2, which of these 2 is more stable? Is the di-substituted more stable, or is the tri-substituted more stable? Okay, the tri is more stable, right? So therefore, what we see is that if we had used, got my numbers backwards. If we used something like a methoxide as my base, I see a 71% to 29% difference between these. So it favors the more stable. And this one is more stable because it has a higher substitution. And that is related to the hyperconjugation. This is known as the CHEM3053 product. And when we have non-steric, right, in non-steric bases, it prefers Hoffman. I mean, it prefers CHEM3053. Sorry, I'm jumping ahead. CHEM3053. Okay, so this is often referred to as CHEM3053's rule. And when we deal with non-steric bases, before product, CHEM3053. That is correct. We get CHEM3053's rule. Now, what can happen is as we increase the steric nature of our base, right, we can change the product percentages. So if we're using something like methoxide or ethoxide, right, we get CHEM3053 products over the Hoffman product. But as we increase the steric nature of our base, we can drive that. So remember when we were talking about the substrate doesn't have a preference as far as regioselectivity, but the base can drive that substrate to be more selective, giving the Hoffman, which is less sterically hindered, favored in large steric products versus CHEM3053, which is ethyl, propyl, methyl oxide. Would all be CHEM3053 product. So the bulky bases that you're going to see, and that's the term we usually use for sterically hindered bases, is just bulky bases. One of the most common you're going to see is T-butoxide, sometimes written this way. You'll also see clean this up, is the diisopropyl amine. Got the lone pair, the base, and then triethylamine. So CHEM3053 is going to be based on the stability. So your non-steric bases, so something like methyl hydroxide, something like NH2 minus, ethoxide, even something like propoxide, right? All of these are going to be non-steric bases. They're going to prefer CHEM3053. We can drive the reaction towards a Hoffman product, which is the least substituted product, by increasing the size of our base, right? So the one you're going to see most often is T-butoxide. Sometimes you'll see it as T-BOC is another way that it's sometimes referred to, right? It's this T-butoxide. So let's look if we take this product, this substrate, let's react it with our methoxide. What are the two products, and then what is going to be the major product? So you start this by looking at your beta hydrogens. Where are all your beta hydrogens? And then from your beta hydrogens, what are your two products? We are running low on time, so let's go ahead and show those. Okay, so if we look at our beta hydrogens, we really only have two non-equivalent beta hydrogens, right? One of those will give us the double bond within the ring. And remember, 6-membered ring is stable because it's geometrically wants to be 100 degrees, and an sp2 carbon is 120 degrees. And then the other elimination, right, is going to be giving us the external. Now, which one of these two is going to be the more stable? This one is more stable. Why? It is a tri-substituted, right? This one is di-substituted. Right? And if we look at our group, it's non-steric base, right? So not a bulky base. That means that this is going to be my major product.